AP Chemistry. We are in Unit 2 reactions. This is the third lesson of Unit 2, and it's on stoichiometry grams. And again, stoichiometry is the mathematics that involves using a chemical equation. It's basically the use of how do we get numbers and actual results from a chemical equation. So we'll jump right into it and you'll see what that means. So in our world, we need to measure things in grams. So that's something that we can measure on a scale, or liters, that's a volume. So you know what a liter bottle of soda or of water looks like, so we measure things in liters. Or molarity, that's something we're not quite ready to define at this point, but it's another measure that we can do in a laboratory. So remember, we have to do measures in things that we can actually see with our eyes, weigh on a scale, feel with our senses in some way. So we are going to talk in this lesson and the next few lessons only about grams, things that we can weigh on a scale. Now down at the bottom we have a chemical equation. It's one that you've seen before. Let me just talk quickly about this equation. It's called a combustion reaction. It's one of the 5 basic types of reactions. And what you're doing is you're taking a hydrocarbon, because it contains hydrogen and carbon, and a hydrocarbon burns. It's used for fuel. This is the simplest hydrocarbon. It's called methane, and it has the formula CH4. And as you know, when you burn something, what you have to do first is light a match to it. The fancy name for that in chemistry is give it activation energy. You have to get it started. You also have to have oxygen. Oxygen is needed to cause something to burn. Just mixing methane, CH4, and oxygen together, it won't start to burn. You have to give it that initial boost, that activation energy, lighting a match. Once you've lit the match, as you know, it will continue to burn. This is the kind of gas that comes out of the outlets in our classroom. It's also used sometimes in transportation, in buses, for example. They use compressed methane. They use methane of some sort. And various other things. Okay, so what it produces is carbon dioxide, which is not a bad thing. It's what plants breathe, and water. Now, you don't see water come out when you burn something, but it's coming out in water vapor into the air. So you don't see it, but it's there. So this equation, what it does is it counts numbers of particles. It's not interested in weight. It's not interested in grams. It's interested in having 1 molecule of CH4 for every 2 molecules of O2. You puts them together to get 1 molecule of CO2 and 2 molecules of H2O. Or we said in our world, we deal in big numbers of molecules called moles, 6.022 times 10 to the 23rd. It could mean 1 mole of CH4 plus 2 moles of O2 gives you 1 mole of CH2 and 2 moles of H2O. We want to deal with these big bundles or baskets of molecules so that we can actually see them and weigh them. But we said finally that the way we really want to view that equation is what it's saying is not some very specific number of moles, not just 1 mole of CH4 for every 2 moles and 2 moles of O2, but you want a ratio. You need twice as many moles of O2, whatever that happens to be, as you have moles of CH4, whatever that happens to be. So if we have 2.5 moles of CH4, we need twice that many, 5 moles of O2, in order to make this reaction work. So that's generally how we view a chemical reaction. But here's the key point to remember. The chemical reaction is interested in numbers, whether you're talking about individual molecules or moles or some ratio of moles of oxygen to moles of CH4. It's interested in a number of particles. It's interested in matching up 1 CH4, whether it's molecule, mole, whatever, for every 2 molecules of O2. It's counting numbers. It's not looking at weight. It doesn't care about weight. So up at the top in our world, we're weighing things in grams. Again, grams is technically a unit of mass. In chemistry, we use mass and weight interchangeably. They mean the same thing in this class. So we can measure things in grams. We can't see a molecule. We can't count a mole. Molecules too small, moles too big. So fortunately, there's a way to get us from something that we can measure, which is the weight in grams on a scale. That's our world. That's what the little children represent. That's our world, things that we can see and experience, to getting them into numbers of particles down there in the bottom that the chemical equation understands, because there's no way we can count numbers of particles. So what is that? What is that big empty space in between the scale up there in grams and the chemical equation below? So first of all, we can use grams to make a conversion into units of moles that the equation understands under the following circumstances. You have to have a pure substance. So pure substance could mean an element like neon or carbon or hydrogen or oxygen, but it can also be a compound as long as it's pure. So water, H2O. As long as you have only H2O, then that's a pure substance. It's not a pure element, but it's a compound, and there's nothing else in that except H2O, except water. So that would be a pure substance as well. CO2, if you have nothing but CO2, carbon dioxide, in your container, that would be a pure substance as well. Okay, so there's nothing else mixed in with it. So that can either be a known gas, a liquid, or a solid. We really haven't gotten into the states of matter in detail, but from 8th grade science, hopefully you know that a gas is like air. It has nothing to do with that stuff that people buy at the gas station for their cars. That's a hydrocarbon compound. There's a whole variety of them that people put in their cars to power their cars. That's called gasoline. It has nothing to do with the word gas as we use it in this class. Nothing. Gas in this class means the molecules are unattached. Think of air molecules or steam when you boil water. You have water vapor molecules. They're floating separately from each other up in the atmosphere. So that's what we mean by gas. It's unattached molecules. Think of them as floating around. Liquid, you know what that is. Okay, a glass of water would be a liquid, and a solid, you know what that is. So if you want to think in terms of water, H2O, the gas would be what we call steam or water vapor. The liquid would simply be liquid water like you would have in a glass of water, and the solid would be ice. That's solid H2O. Okay, so we need a pure substance. So how do we get from grams of these pure substances down to the land of moles? That little animal, by the way, is an animal called a mole. So that has nothing to do with why we use moles in chemical equations. It's just meant to as a little picture, a little reminder. Okay, so what we need is a translator. We need to get us from grams down into moles, because we speak in the language of grams. We can measure that on the scale, but the chemical equation is interested in numbers of particles, and we're going to use these big baskets called a mole. So we need a translator to get us from grams to moles. That translator is called the molar mass conversion. And you kind of have to burn that into your memory, that phrase molar mass. Molar means mole, and mass means grams. The mass is measured in grams. So molar mass means you're converting from grams to moles or from moles to grams. And so that's our translator. You can think of it as grams is the Spanish language and moles is the English language. And if you have two people and one person speaks in Spanish and one person speaks in English, but they don't speak the other language, you need a translator. You need somebody who speaks both languages to translate for them. So what we have are these molar mass conversions, fortunately, to allow us to convert from grams, which we can measure in the lab, into moles, which the chemical equation speaks in. And then once we've used the chemical equation to figure out what we're trying to figure out, we can go back in the other direction. We can use the translator to take us from moles, which the chemical equation is working in, again, numbers of particles, numbers of molecules, numbers of atoms, back into grams, which is something that we can use in the laboratory. Okay, so the molar mass equates 1 mole to some number of grams. So in the case of carbon, as an example, if we were using just carbon atoms, you can see that molar mass in blue is saying that 1 mole of carbon equals 12.01 grams of carbon. We're no longer interested in atomic mass units and individual molecules. We're interested in moles, okay? So that's a molar mass conversion. It equates the number of moles, that's the number of particles that the chemical equation down below understands, with the number of grams, which we, in our world, measuring on a scale, understand. So that's the translator that gets us from our world of grams to the chemical equations world of moles, or the other direction, from the chemical equations world of moles, of numbers of particles, back up to our world of grams, okay? So pause if you need to and think about that. What's going on here? Be sure you understand what we're trying to do and why. So up at the top, you have a problem. How many moles of CH4 are required to form 8 moles of H2O? So you do what we did in the Usain Bolt problem, or in the problem where I had all the student names. You don't even really have to understand what a mole and a gram is or anything. You just have to know how to cancel units to set you up. So this is a graphic organizer that you're going to use as a beginner. And what it has is up on the top there in that top row are numbers of grams. So if you're given a number of grams or you're asked for a number of grams, you're either going to start or end in that row. That's our world in grams. Down in the blue dashed line is the chemical world. That's the world that the chemical equation understands. It's numbers of particles, numbers of molecules. Either a molecule, a mole of molecules, or some ratio of numbers of methane to numbers of oxygen, what we talked about. So we need to get from our world down into the chemical world. In order to do that, we need the translators. So for CH4 methane, 1 mole equals 16.04 grams. Okay, that's what you worked on in the last lesson, is how do you figure that out? You take 1 mole of carbon, that's 12.01. You get that off your periodic table. And from now on, instead of atomic mass, those numbers below each element, we're going to call them molar mass. I want you to think in terms of moles. We really don't deal on the atomic level. It still really is called atomic mass, but I want you to think of it as molar mass. So carbon has a molar mass of 12.01. That's straight off your periodic table. Be sure you can locate that. Hydrogen has a molar mass of 1.01 grams, and you have 4 hydrogens. So 4 times 1.01 is 4.04. You add that to 12.01, and you get 16.05 grams for 1 mole of CH4, of methane. Oxygen. Now, oxygen appears in nature. We talked about this as a diatomic molecule, O2. It never appears in nature as a gas, as just O. So you have an O2. So if you look at your periodic table, a single oxygen atom has a molar mass of 16, and 2 of them would be twice that. It would have a molar mass of 32. So 1 mole of O2 molecules is 32 grams. CO2, same thing. Carbon is 12.01. Oxygen is 32 for the 2 O2s. You add those together, you get 44.01 grams for 1 mole of CO2. And finally, H2O, 2 hydrogens, that's 1.01, and you have 2 of them, so that's 2.02, plus the 16 for the oxygen. In the case of water, that is just a single oxygen atom. That's going to be 18.02 grams for 1 mole. So that's our translator. It gets us from the grams, that's our world that we measure in, into the world of the chemical equation, which measures in numbers of particles that we otherwise would have no way to be able to count or be able to see. And that's the beauty of the translators, called molar mass conversions. Then it also gets us back out from the chemical equation, back into our world, going from moles back to grams. So let's go ahead and work this problem. Now this problem, this first one for today, these are going to be very simple. We're only going to go from moles to moles. We're going to have nothing to do with grams today. So you're seeing that it's asking how many moles of CH4 are required to form 8 moles of H2O. Okay, so the first thing is, what are we looking for? What's the question asking for? And you see down in the red box on the lower left, a question mark appeared. We're trying to find moles of CH4. So you see that we're in the column for CH4, and you see that we're down in the row, down inside the chemical equation, that's the row of moles. Everything in that blue dashed line is the chemical world, that's in moles. So that's what we're asking, trying to find moles of CH4. And then it's saying are required to form 8 moles of H2O. So that's what we're starting with as far as the equation. We go over there to the right, we go to the H2O column and the moles row, which is in the chemical world. Right there, we put the 8 there. Now, if you look at the chemical equation, you're starting on the left with CH4 and you're ending up on the right with 8. In other words, the chemical equation flows from left to right. But our math equation is flowing from the 8 over to the question mark, because we start with what we know, 8 moles of H2O, and we end up with the question mark. So simply what's going on there is that we're trying to find, the unknown we're trying to find is over on the reactant side, it's CH4, and what we're given to start with is 8 moles of H2O. So we're trying to answer the question, how many moles of CH4 do we need to produce those 8 moles of H2O? But the math equation is going to go from the known 8 to the unknown question mark, so from left to right. So it's going to look reversed of what you're seeing, this arrow here. So let's go up and let's put those in our equation. So there's the 8 moles of H2O. That's what we're starting with over on the left. And when you write these, you're going to hear me say put this way over on the left of your sheet of paper, and then what you're looking for, the question mark, put way over on the right, because you don't know how many conversions you're going to need. Today you're only going to need one. Keep it pretty simple. So there you go on the right. So your math equation is reversed from what your chemical equation is down there. It's not always that way. It just happens to be in this question. You go from known to unknown in the math equation. So you're trying to find some number of moles of CH4 that's going to produce 8 moles of H2O. So there's the equivalency. 1 mole of CH4 equals 2 moles of H2O. Notice you don't need a molar mass conversion. We're not going from grams to moles or moles to grams. We're simply working inside the chemical world right now. For this lesson today, we're only working inside chemical world. So you're going from 8 moles of H2O to some number of moles of CH4. So you're staying inside that blue dashed line. You're not going outside of it today. You will tomorrow. But there's the equivalency. So the equivalency is simply the coefficient that's in front of CH4 equals the coefficient in front of H2O. In other words, 1 mole of CH4, for every 1 mole of CH4 you combust, you burn, you're going to end up with 2 moles of H2O. Again, those letters in parentheses are the state of matter. So the CH4 and the oxygen are in gas form. The CO2 is in gas form. The H2O is in liquid form. All right, so now we got to simply find a conversion from that equivalency. So again, understand a moles to moles equivalency. It's simply the coefficient in front of one of these substances that you're interested in and the coefficient in front of the other. So it's 2 for moles of H2O and 1 for moles of CH4. You simply use those numbers that are the coefficients. So now we're going to make 2 conversion factors out of this equivalency. How do you do that? You know how to do that. You put one of them over the other. 2 moles of H2O for every 1 mole of CH4, or 1 mole of CH4 for every 2 moles of H2O. So you've seen this before. So now we have to ask ourselves, which of those goes in that box up above? So think about it. Which one are you going to put in that box? You need moles of H2O to cancel and moles of CH4 to appear in your final answer. So the answer is, it's going to be the one on the right. 1 mole of CH4 over 2 moles of H2O. Again, why is that? Because you need moles of H2O to cancel out, and you need moles of CH4 to be your last man standing that shows up in the final answer. So we cancel that, and the last man standing is the moles of CH4, which ends up over as your units in your final answer. So now that you have your units set up properly, everything cancels except the one you want in your final answer, you're ready to do the math. So it's going to be 8 times 1 divided by 2. Okay, and that would equal 4. And there it is. So 8 moles of H2O, to produce 8 moles of H2O, you require 4 moles of CH4. So we can go down to the bottom to our graphic organizer if you so choose. You already have the answer, but you can replace that question mark with a 4. And there it is. So it takes 4 moles of CH4 to produce 8 moles of H2O. Why? Because for every 1 mole of CH4, you're going to get 2 moles of H2O. For every 2 moles of CH4, you'll get 4 moles of H2O. For every 4 moles of CH4, you'll get 8 moles of H2O. You're always going to get twice as much H2O out of this reaction as you started with moles of CH4. So the problems you're given today are pretty simple, straightforward. They're just converting moles to moles. It's a single step conversion. You notice we only have one box up there. And so that's how you do these problems. Tomorrow we'll get into the grams, converting grams to moles and so forth in the next 2 days. Okay, that takes care of this lesson. So you have some problems on your problem set. And this is actually a fairly quick problem set. Not going to give you a lot of these. I think you'll get the concept quickly. So use today to catch up on earlier lessons, okay? All right, so we'll see you on the next lesson.